This is Grace Chapman, and this is my Lab 3 for Physics 2. Introduction. The procedure for this lab was to use a magnetometer to record magnetic field at different distances from a bar magnet. We measured on-axis and off-axis magnetic field. The physics concepts used are the concepts of magnetic fields, distance dependencies, and bar magnets. For example, in the lab, the further that the magnetometer was away from the magnet, the smaller the reading on the magnetometer. This shows the distance dependency of bar magnets in their corresponding magnetic fields. The main result from this lab was the magnetic dipole moment, which was shown to be 46.23, 12.59, negative 68.53 amps meter squared. When the magnetometer is far away from the magnet, it measures a near-zero magnetic field in the x direction, and as it moves closer to the magnet, the measured x component of the magnetic field increases. So these are the two statements that describe what I observed in this lab. How did we actually solve for the magnitude of magnetic moment? This equation is most accurate far away from the dipole, and it's the equation that was used in the coding portion of the lab. I recorded the results from the physical component of the lab in an Excel table, and here are the main results. The magnitude of magnetic field measured by this Excel document, or calculated by the Excel document, shows that the x component is 46.23, the y corrected component is 12.59, and the z component is negative 68.53, which is almost exactly what the result was from my coding, as we will discuss later. This is the graph that I got from the Excel document, and it shows a very linear relationship between the natural log of the magnetic field x component and the natural log of the distance between the magnetometer and the magnet. So it shows this very linear relationship between the two. For the coding portion of the lab, I wrote a function that is shown on the bottom left-hand corner of the screen that is called dipole B and calculates the magnitude of magnetic moment of a dipole. This is what the rest of the code looks like, and it ends up creating a picture shown here with 6 arrows in the 6 main directions from this middle white, which is represents the bar magnet. The orange arrows show the on-axis magnetic field, and the blue arrows show the off-axis magnetic field. These values are almost exactly the same as the averages from the Excel table, so the coding results and the physical results compared very well at the same distance. The magnitude of magnetic moment here, as I said earlier, at 45 degrees at a distance d is 46.23, 12.59, and negative 68.53. All of these arrows are pointing away from this magnet to show the overall magnetic field. Conclusion. What if I hadn't oriented my experiment to compensate for magnetic north, but had instead laid out my meter stick at some intermediate angle with respect to Earth's magnetic field? How would my results have changed? I wouldn't have had a correct 0. Every value would have been off by some constant because the magnetic north would be continually affecting the results from this experiment by a constant value, because, as we know, the Earth's magnetic field isn't going to be changing, but the magnetic field created from this magnet would be the only thing that would be changing, so it would just be off by some constant. What if I stuck 2 identical magnets together into N and ran the experiment again? I would expect the values to double because there would be a magnetic field that was twice as strong. So therefore, if I had 3 magnets together or 4 identical magnets together, I would expect a linear relationship between the number of magnets together and the magnitude of the magnetic field. So finally, again, my main result from this lab, which was consistent from the coding and from the physical experiment, the result is that the magnitude of dipole moment is 46.23, 12.59, negative 68.53 amps per meter squared. Thank you.